Okay, so hello. Starting Unit 7, we are going to talk about differential equations. And I will continuously use this idea of differential equations. I won't necessarily say the word ordinary, that's kind of unique to this textbook. Some other keywords that we're going to be doing are verifying. A verifying is really just making sure that an original equation is the solution to a differential equation. I'll show you that in the first couple examples. Some other vocab: general solution and particular solution to a differential equation. So a differential equation is simply when we have an equation written as dy dx, or we could also have d squared y all over dx squared. And we are going to be solving these differential equations. And when we solve these differential equations, let's put solving. We are going to integrate to get back to an original function. And so there's some words that we will be seeing both in the homework and on an AP test that we really have to pay attention to. This idea of ordinary, I'm going to just talk about it because the book talks about it really quick. An ordinary differential equation is an equation involving an independent variable x. You can read through the rest of this, a dependent variable y, and the derivatives of y with respect to x. So these are all ordinary differential equations. So there's some differential equations that have y prime, Newton's notation, and also Leibniz notation. In this next slide, the order. So this slide is going to be important again for this textbook. There's first order and second order and third order differential equations. So whatever derivative is present and is the highest order, that's going to determine the order of the whole differential equation, almost like polynomials. So again, here's first order differential equation. This is also a first order differential equation. Now I'm going to come down to this point down here because this says take the first derivative and square it. It's not saying the second derivative, like this is a second order derivative right here. This is a second order derivative here. And then a third order derivative is like this one right here. So think of this like position, velocity, and acceleration again. The next slide I'm just going to kind of skip through. It is going to talk about determining based off of the order, whatever is the highest order, that helps you determine your degree. I think some of this is a little confusing at the end. So I'm going to go to this example here. In this example, again, some just formalities about defining a differential equation, and more specifically, a linear differential equation. So if I look at my differential equation that's present, this differential equation that is here is, because we have this is going to make it a second order differential equation. And because it is a second order, that will help us determine the degree. So we look at the x power, and then the degree of the differential equation is a 2. Honestly, I've taught in many calculus books before. We never really focused on the degree of the differential equation, just the order. So when we classify differential equation, this is called, like I said, a second degree or second order differential equation. Oh, whoops. It is, I don't know why it's saying of degree 1, so I should take that back. That's why it's a little misleading. The degree, even though it says x squared, it's considered a linear differential equation because of this, each derivative that is present, and the variable y, if present, is raised to the power 1. So if we see the differential equation and we see a y within it, that's going to give us a power of 1. Really, what I want you to take away from this is that this is a second order differential equation. Okay, so we've already in previous sections talked about a solution to a differential equation. We have two types. We have a general solution. So the general solution would be if we have something like y is equal to x squared plus 7x plus c. It is that constant of integration. And then we also have, in this next slide, a particular or specific solution, which we've also had before. And a particular or specific solution will have some information so that we can get rid of this arbitrary constant of variation. So again, your book will call this arbitrary constants, and I have used the phrase constant of integration. I may have said variation, which also exists in math classes, but that's a constant of integration or arbitrary constants. Okay, so this is very typical on an AP test. We are only going to do part A, where we have to verify. So directions on a multiple choice might say verify that a function is a solution to a differential equation. So there's two different ways we can approach this. We could start with the differential equation and integrate and go backwards. Or what we can do is almost like a linear idea, where you might have to check to see if something is a solution to a linear system. So kind of watch as I move through this. I'm going to do this in like 3 steps. I am going to start with the step of starting with the original. So I'm going to start with the original function that is given, that f of x. I'm going to write it as equals y. I'm going to reverse it. Then I have the 4x, or x to the 4th minus 5x plus 1. If I need to find y prime using my power rule, here is what I'm going to get. And then I'm going to do y double prime, which is 12x squared. So that is the first and second derivative. And I'm given this second derivative right here as well. So I am going to verify now by substitution. So think of it, like I said, like if we had a system of linear equations and we had an x and y coordinate and we'd plug in a value for x and then plug in a value for y. Or if we have 2 linear equations and they're both y equals, we set them equal to each other. So I'm going to take what I have right up here, and I'm going to write that down. So this is my y double prime minus 12x squared equals 0. I also know by up here that y double prime, it's almost like this is the input, and then this is the output here. So I'm going to plug in for y double prime 12x squared. When I do that, I still have minus 12x squared. And then I'm verifying that 0 is equal to 0. You may get some questions, and I might try to find some AP questions where you have to use both y prime and y double prime, and maybe even y triple prime, and do a multiple substitution. So I like to say do this in 3 steps. Start with your original, do your first and second derivative, maybe even your third. Then you're going to do substitution. And then because it says basically we have to it says verify. So I'm just going to make a conclusion because the notes in the book kind of do this as well. They say because of this work that we did, and when we do substitution down here, it's almost like if you have an inverse and you plug in an inverse to the original function and you end up getting x at the end, you verified that they're inverses of each other. So I'm just going to say y is equal to, because it says verify that this is a solution. So I'm going to say conclusion, y is equals f of x is a solution. So you just have to get to this part where you're doing some substitution and making a true statement. Okay, so now this, again, is probably more of what you would see on this up here was probably more of a multiple choice FRQ, or sorry, multiple choice on the AP test. This is an FRQ. Very, very typical. Verify that we have this equation, and it is a solution to the differential equation. One other thing I think before I go, nope, it's in the next example. So I'm going to take this equation and I am going to write it again. And I am going to implicitly differentiate in hopes of getting this. So let's erase that. I'm going to implicitly differentiate. I'm going to write that in red. Implicit differentiation, which involves other types of differentiation, power rule, chain rule, product rule, quotient rule. So in this one, I'm going to use power and product rule because I have a product right here. So when I do my implicit differentiation, I am going to do 2x dx minus, now I have a product. I'm going to do 1, then d2, I'll do in red. The derivative of x to the third is 3x squared. And then that is in terms of x. Oh, sorry. I did it backwards. I said it differently. Let's fix that up. I'm not going to worry about changing colors. So I'm going to do 1, then d2. So I have to do the derivative of y, which is dy, plus 2, which is y. So here's 1 and here's 2. 2 d1, and I did that with respect to x. Now I put that whole thing in a quantity because it is a product of 1 times 2. This looks a little confusing here, so I'm going to get rid of it. And then I also have to do the derivative of the 12y to the third dy. And then that's equal to 0 because c is a constant, so derivative of constant is just 0. Referring back to implicit differentiation, what we did was we divided all differentials by dx, or all terms, simplified, and this would be 0 over here. And I am going to do a couple things at once. I'm going to factor out a dy dx. And then if I distribute at the same time here and here, and then I know that this also has dy dx here. So I'm going to write plus 12y to the third. That's going to equal, because I have a negative x to the third, I'm going to move that over to the other side. That dy dx, that negative x to the third went with the dy dx. I apologize. I'm going to move over this negative 3x squared y. And it was a negative, so it is a positive actually. Bear with me. It's late at night right now for me. And then, so maybe what I should do is I'm going to highlight those two things. This will go to the other side, as will this. And then I'm going to write minus 2x behind that. Then solving for dy dx, I'm dividing by this quantity. I don't need the parentheses, I suppose. And hopefully, as you can see, we end up with dy dx is equal to, I'm going to write it so that I've got a positive lead coefficient, which you don't have to, you just have to recognize that they're equivalent. And hopefully you can see that it is the same expression or quotient as was presented at the original part. So this is very typical, these like almost verbatim directions verify that this is a solution to the differential equation. Then what will happen is you will take this and sketch something called a slope field, or you will have to find a particular solution from here. All right, we are going to do, let's see, we're going to do one more, and then example 5 I'm definitely going to have to do in class because I don't want to make this any longer. Notice it says general solution to this differential equation. So what I'm going to do is I'm going to take my differential equation, I'm going to rewrite it, and I am going to solve the differential equation. When you solve a differential equation, you are going back to the original function. So when you solve a linear equation, you get back to x equals. So now what we're doing is we're getting y equals, or f of x equals. We're going back to an original equation. To do that, I am going to separate the differentials. I'm going to put dx on both sides. And when we get into section 7.2, we'll do this even more so. I'm going to put a dy here. That's going to equal 6x squared plus 5. And then dx at the end. We are going backwards, so we're going to integrate. We have to take our derivative, differential equation, get back to the original. So I'm going to introduce the integral symbol on both sides. Properties of equality allows me to do that. This is called separable differential equations. Then what I'm going to do is actually integrate. So if I go to the right side, I'm going to add 1 divided by the sum. That's going to be x to the third. 6 divided by 3 is 2, plus 5x here. And then I know I have plus c. Over on the left side, there's a 1 here. So if I integrate 1 dy, it is y. And I could put plus c, but I'm going to gather all the plus c's on the right side with the independent variable. C is just a constant of integration. This right here, and I think we've had this type before, this is a general solution. This describes the family of functions whose derivative is this. So this is the general solution we've solved. Then for part B, so that was part A, part B, when we find the particular solution, with the boundary condition, again, unique to this textbook. I don't know why they do it, but it is an initial condition. So initial condition, I think they say the word boundary because maybe that ordered pair is on the graph. I'm not sure why they use the word boundary. I think it's a little confusing. So what I'm going to do is, just like when I verified, I'm going to substitute. So I'm going to substitute 1 for x and 10 for y into my general solution. And I think we've had this before. 10 is equal to 2 times 1 to the third plus 5 times 1 plus c. 10 is equal to 2 plus 5 plus c, which is 7. So c is equal to 3. Then we have to put that back into the general setup, but replace the c with a number 3. So this is the specific solution whose differential equation, dy dx, is 6x squared plus 5, and that solution passes through the point 110. I think we can probably do one more, so you have this for reference. We're going to do the same thing here. So for part A, we're going to find that general solution by solving. I'm going to take that differential equation and I'm going to move the dx to the other side. Now, these will definitely get more complicated in section 7.2. I'm moving that dx to the other side. I separated my differentials. I am going to integrate both sides by properties of equality. That will result in just y on the left side. When I integrate e to the x, I get e to the x. I could do u substitution here if I wanted to. But as I get better at this, I can see u will be 2x. du would be 2 dx. I have to divide by 2. Derivative of, or I should say, integrating sign is a negative cosine. So this is going to be minus 2 cosine of 2x. And then I will have plus c. That is my general solution. Now my initial condition, now the book says it here. So my initial condition, I'm going to substitute. And I will have 0 for x and 4 for y. That will give me 4 here equals e to the 0 minus 2 cosine of 0 plus c. C will equal 5. So the particular solution or specific solution, sometimes you see, will be y equals e to the x minus 2 cosine of 2x plus 5. Like I said, we'll probably do these in class. These are just going to get a little bit more challenging as we progress through Unit 7.